Welcome everybody to the 20th edition of our GO2NE Global Ocean Oxygen Network webinar series. I am Andreas Oschlies from GEOMAR at University of Kiel, Germany. And on behalf of the entire GO2NE team, I'm very happy that you took the time to be here, well, with our incredible speakers this morning, afternoon, evening, no matter where you are. Before starting, we would like to bring your attention to the Deoxygenation newsletter. So that's here. You can see it on the left. It's very small print. If you want to see it in real size, you scan the QR code on the right. And if you're on Twitter, you can also use the handle down there and be informed about new activities of the Global Ocean Oxygen Network and Global Ocean Oxygen Decade Program, UN Decade Program activities. The next GO2NE webinar will be in July, so very soon as well. So stay tuned and register for the next one as well. Some quick housekeeping. You have the possibility to type in your questions into the Q&A box. And the chat can also be used to share additional information if you have logistical problems. Questions, the question box, please, and we will address those after the talks of the speakers. The speakers have 20 minutes and we have 10 minutes Q&A. So let's get started with two fantastic speakers today. It's the first time we also have speakers from industry and publicly funded research at the same webinar here. And this is a special occasion. I very much look forward to this. And we start with Patricia Handmann. Stop sharing here. She's a physical oceanographer by training, did her PhD and postdoc at GEOMAR Kiel, did a lot of seagoing expertise and looked at deep water formation during her PhD and postdoc time. Now she's at Lhyfe, the company in Nantes in France, where she's the oxygenation advisor. And Patricia, I very much look forward to your presentation.
Yeah, thank you for the nice introduction. So today I have the immense pleasure. Can you see my screen?
Yes, perfect.
Okay. So today I have the immense pleasure to present a talk about the potential environmental services of offshore hydrogen production. And namely, we will focus on ocean reoxygenation today. If we think about the world population, 40% of our global population live within coastal areas, so within 200 kilometers from the ocean shore, and 12 out of 15 megacities are coastal. The predictions of the United Nations for the global populations are hitting 11 billion people in 2100. And this means that there will be an increasing hunger for energy, food, and drinking water. And of course, our lifestyle is always connected to CO2 emissions. So since the Industrial Revolution, we are emitting CO2. And we are emitting it so fast that the concentrations since the 1960s increased by 100 ppm. And these are really levels, so levels above 400 ppm, which haven't been so high in the last 800,000 years. And they are rising so fast. This rise has not been so fast in the last 2 million years. And of course, this leads to a temperature rise in our atmosphere, as shown on the right-hand side. There you can see a temperature plot, constructed temperatures in our Earth's history. And the little green box shows where our human species emerges. So 300,000 years ago, Homo sapiens emerges. And then the last 11,000 years, we adapted to really nearly constant temperatures. So what we are doing right now is we are changing our climate system. We are changing Earth's temperatures. And this was again underlined by the IPCC special report that was published this year, showing that we already are facing a temperature rise of 1.1 degrees Celsius in 2023. And of course, this warming is not only going into the atmosphere, but also into the ocean. It's actually 90% of this warming going into the ocean because ocean water or water has a really high heat capacity. And this heat is not only going into the surface ocean, but also into the deep ocean. Actually, a significant part and contribution is found in the deep ocean. And of course, this ocean warming has a lot of impact on our climate system. And this is not only on the amount of evaporation or the melting of sea ice or melting of the ice sheets. It's also found in the decrease of the oxygen levels in the ocean. So we are facing really three major stressors right now, which are ocean warming, acidification, and ocean deoxygenation. And all of those three are interlinked, they feedback on each other, and they are really connected by complex interactions. And now, of course, we want to focus a little bit more on ocean deoxygenation. And I have to show this plot by Denise Breitburg here from 2018, which is showing the low oxygen zones on our planet. In blue, we can see the oxygen minimum zones that are really linked to the eastern upwelling regions, which are dynamically driven by the local dynamics. And those red dots here that show coastal hypoxic or low oxic sites. And they are really due to a mix of eutrophication and slow circulation, where eutrophication is really linked to enhanced nutrient input from land sources. So our ocean is losing oxygen. And this is really due to an imbalance between the processes that supply oxygen, so the biological or the physical pump that supply oxygen to the ocean, and of course the processes that use up this oxygen. And this deoxygenation, so this losing of oxygen, is getting even worse with the ocean warming and eutrophication. And ocean warming here really having the impact on the global current system and on the stratification, increasing the stratification between surface and the lower water column. And eutrophication is really linked to the enhanced input of nutrients, which is linked to our agricultural industry or sewage input. So everything that's coming from land sources. And it has been observed that the upper ocean has already lost 0.5 to 3% of oxygen since the 1970s and is predicted to further lose oxygen in the future, between 1 to 7% of the global current inventory of oxygen in the next 100 years. And of course, this deoxygenation has an impact on our Earth's climate system, again, in a feedback loop. Because anoxia and sulfidic conditions, which are linked to anoxia in coastal ecosystems, for example, can increase the production of greenhouse gases, and namely nitrous oxides. So the question would be really, what could we do to counteract ocean deoxygenation? And these are really boring facts. It's the same measures as against global warming. So to keep global warming below 1.5 degrees Celsius. So we need to decarbonize our lifestyle, the industry, and actually need net negative emissions. And on the other hand, we need to control nutrient pollution. So we need to decrease the nutrients that are input into the water column. And of course, those nutrient limits have to be put in by policy. So there has to be sewage control of wastewater treatment facilities, for example, and there has to be control of fertilizer usage of the agricultural industry. And also there can be land management measurements put into place, where, for example, buffer zones are planted around agricultural zones in order to absorb excess nutrients in order to keep them from getting into the aquatic ecosystem. And so this is really only possible if all stakeholders work together and are included. That means science, the politics, population, and the industry. So we need to work together in order to make this work and to abate climate change. And of course, climate change is also connected to the biodiversity crisis, which means that we are losing biodiversity and space for living organisms. And this is really on the left-hand side effect, one of the 15 facts on the GO2NE website, which is saying that steps required to slow or reverse ocean deoxygenation can directly benefit marine biodiversity and human health and well-being. Because studies have shown that an ill ocean or a sea ecosystem really has an impact on human health as well. And on the other hand, the Kiel Declaration from 2018, which says that strategies to slow and eventually reverse deoxygenation and its ecological impacts need to be co-developed between science and societal actors. And so as a company, Lhyfe, we are producing hydrogen. We are asking the question what the potential of artificial ocean reoxygenation could be on a short and long term. And of course, if we remember the title, it's really offshore hydrogen production, and offshore hydrogen production is always linked to the production of renewable energy if you want to produce it sustainably. And so this is why I'm showing you here a map of the global offshore wind speeds. So the energy production with wind turbines is possible if the mean wind speed is around 8 meters per second or higher. And these are really those red regions on the map here. And estimates from the International Energy Agency show that by using, if we would use all this potential today, we would cover the total electricity demand of the world 18-fold. So there's a huge potential there. And the potential, to put it into gigawatts, would be 71,000 gigawatts. And just to put that into relation, 1 gigawatt is about the production of one nuclear power plant. So it's a huge potential that we find offshore. But there's always the problem how this energy is then distributed. So how can you get this energy from the offshore production sites to onshore industrial sites or transportation or whatever? So one could be via cables. So really a cable system between the wind park and the shore. Or second could be through a pipeline system as hydrogen gas. And here we are really coming to the sustainable green hydrogen production offshore. So hydrogen could play a really important role if you think about industrial sectors that that are really hard to electrify, such as the chemical industry, metallurgy, like the iron production, glass industry or cement industry. So here, hydrogen could actually play a really important role in order to decarbonize the industry. And of course, if we want to have sustainable energy production, we need to use wind or solar energy. And just to give you a feeling, if you would have a 500 megawatt electrolyzer, it could produce 200 tons of hydrogen a day, but it would also produce 8 times this mass in oxygen due to the molar mass of hydrogen and oxygen. And of course, an electrolyzer is using water and then splits that into hydrogen and oxygen. This is why we have the surplus as a byproduct in oxygen. And we actually need this green hydrogen production, because if you think about the way how hydrogen is produced today, 98% of hydrogen is produced on the basis of natural gas. And 1 kilo of hydrogen of this gray hydrogen is emitting 11 kilos of CO2. So it's not really decarbonizing anything. If you think about hydrogen produced by electrolyzers with water, for example, offshore, then we would produce it by emitting around 1 kilo of CO2. But this is only 2% of the overall production of hydrogen today. So there's still a road to go. And how could offshore hydrogen production look like? So on the bottom, I have two pictures for you. On the left-hand side, it's the Sea Lhyfe. It's the world's first offshore producing hydrogen platform, which is installed near Nantes. And on the right-hand side is a fixed platform, which is an offshore feasibility study that could be within a wind park, for example. So with all of that potential that we've seen now for offshore wind energy, we asked the question in collaboration with a research group at Ifremer in Brest, what the responses of the oxygen minimum zones could be if we would reoxygenate the global ocean on an industrial scale, really linked to this offshore wind potential that we've seen 2 slides ago. And for that, they used an global ocean model, a NEMO model with a resolution of 2 by 2 degree and 31 Z layers. And of course, it was forced with the climatological atmospheric forcing. And in an additional experiment, this model was then coupled to the Piskus model, which is really a biogeochemical model reproducing basic biology and biogeochemical cycles. So overall, 3 experiments were done. One was only the physical experiment without any oxygen input. The second was the physical model with the oxygen input at those orange spots on the right-hand side on the map, where the oxygen is only used as a physical tracer, so basically advective transport of oxygen. And then a third experiment was done where the NEMO model was coupled with the Piskus model, so the oxygen is input at those orange spots on the map and can then also interact with the biogeochemical model. And the experimental scenario was looking like this. So all those orange spots represent around 18,000 production units, where each production unit is producing 70,000 tons of oxygen a year. If you calculate that in relation to what the biogenic oxygen production between 0 to 150 meters in a control run could be via phytoplankton, of course, this would represent 0.86% of the biogenic oxygen. The injection was done at 150 meters because this is really close to the upper limit of most of the oxygen minimum zones. And then a 100-year-long experiment was run. And over those 100 years, if you calculate the total amount of oxygen that would be input by all of those industrial stations, that would amount to 1/30 of the global demand of oxygen over this time, where the relation is really here taken to CMIP estimations. So what was found was that the oxygen inventory increased by 0.07% with respect to the control run in this coupled run with the Piskus model. The overall volume of the oxygen minimum zones reduced by 1.1 to 2.4%. And this varying percentage here is really dependent on the definition of the oxygen minimum zone. So oxygen minimum zone can be defined by 80 millimole per cubic meter concentration or by 50 millimole per cubic meter concentration. So this is why there are 2 different numbers here. And then it was also found that there's a slight deepening of the upper oxycline of all oxygen minimum zones. But the global average really hides regional disparities. And this is why there are those 2 plots on the bottom here. They are showing in red to blue the percentage of oxygen concentration. So this is really the difference between the coupled model and the control run in percentage of the control run. And then there are also the concentrations marked in pink and in green, who really show that in the Atlantic we get a shrinking of the volume of the oxygen minimum zone here. So this is really a meridional section along 2 degrees east through the Atlantic. And on the right-hand side, this is a meridional section through the Bay of Bengal along 90 degrees east. But those 2 oxygen minimum zones really show different patterns in the percentage of change. So we will have a closer look onto that. So the regional results, their responses really vary. If you now look onto the map on the left-hand side, you can see that they are green to blue colors, where the green colors really show regions where the biochemistry is dominating the response to the artificial oxygen input. And the blue areas really show the advective transport dominated response. And here you can really see that the Bay of Bengal and the Atlantic, one is green and the other one is blue, are really dominated by different processes. For the Bay of Bengal, we can really see that in the lower part of the oxygen minimum zone, the deoxygenation really increases. And this is really due to the changes in the biogeochemical cycles, namely the nitrogen cycle. So here the effect is really that the oxygen input reduces the denitrification in the water column, which leads to more nitrate availability, which enhances the net primary production, and therewith increases the vertical export of particulate organic matter. And of course, the bacteria remineralizing this organic matter is then decreasing the oxygen concentrations because they are using oxygen in order to remineralize the organic matter. And on the other hand, the deep nutrient stocks are also increasing. Also, there is a shift between the limiting nutrients because there's more nitrate available. This really shifts the nutrient limitation from nitrogen to phosphorus. If you now focus on the Atlantic, so on the right of the globe that is shown on the left-hand side, the Atlantic is really blue. So here we've seen that there's a decrease of the oxygen minimum zone value, really due to the advective physical transport of the oxygen into the zone. But also you can see that there are only input stations from South Africa to the north of Namibia, but the effect is really downstream from them, so towards the equator. And this really shows that artificial oxygen input has non-local environmental effects on the ecosystems around. So this really calls for high-resolution regional experiments and also for the definition or the question, what kind of regions could benefit from artificial ocean reoxygenation? And so I want to focus now more on the European shelf seas, so the North Sea and the Baltic Sea, which are really shown here in a larger plot on the top. And they are really suffering from eutrophication on a permanent or on a seasonal basis. And most of these ecosystems are really defined by a limited water exchange, a weak circulation, and a strong stratification, which is, of course, decreasing the mixing between the upper part of the water column and the lower part of the water column. Then most of these waters have hypoxia or even anoxia. That means very low oxygen or even no oxygen in the bottom waters on a permanent or seasonal basis. And they feature a lot of the time processes in the sediment that lead to further oxygen loss. And for example, in the Baltic Sea, the sediment under anoxic conditions starts to release phosphorus, which again has a positive impact on the eutrophication of the Baltic Sea. So it increases the eutrophication and then leads to a vicious cycle of further oxygen loss. And of course, for example, the Baltic Sea is already suffering economic loss in the height of billions of euros due to the loss of biodiversity, marine life loss, and also the loss for tourism and also livelihood. Now, the question would be, is the potential of hydrogen production enough in order to supply those regions with oxygen? And if you look at the marine spatial planning for those waters here, we find that the planned wind power installed by 2030 is planned to be 60 gigawatt for the North Sea and 22 gigawatt for the Baltic Sea. And of course, this could be then linked to electrolyzer capacity. For the Baltic Sea, there is no official numbers for that yet, but for the North Sea there is. And they plan to install 20 gigawatts of electrolyzer capacity. And this is not only offshore, but also onshore capacity. So there would be enough potential for the Baltic Sea, for example, to produce hydrogen and its byproduct oxygen. If we now focus on the Baltic Sea, we find, and this is really taken out of the Helmholtz report, that the area of hypoxic and anoxic regions in the Baltic Sea are continuously growing since the 1990s. Even though since the 1990s, nutrient abatement strategies, meaning limiting nutrient input into the Baltic Sea, were put into place. So the Baltic Sea could maybe profit from artificial ocean reoxygenation. If we now do a back of the envelope computation, we find that by the demand of the Baltic Sea, which is between 10,000 to 15,000 tons a day, and this is really taken out of published literature, we would need around 9 to 10 500 megawatt platforms to really fulfill this oxygen demand. But this is really theoretical, and if we ask the practical questions, we really start to get into transdisciplinary swamp of questions. And they are really about the technique, how we oxygenate, where we do oxygenate. Is there any strategies that could be really beneficial to the ecosystem? What are the possible risks, and so on? And they finish with really legislative questions, like how the observational strategy is organized, who is paying for it, and what happens with the downstream effects if the oxygen is, for example, getting into the territorial waters of another nation. So this is also really a legal question. How could reoxygenation be included as a seabed measure in existing eutrophication abatement strategies? And I would like to leave you with this summary slide here, and I am open for questions.
Wow, yes, very excellent. Thanks a lot, Patricia, for this exciting and stimulating presentation. Also starting from deoxygenation, why it matters, where it matters, and what could be one possible contribution to solutions. We have a few questions already. If you have more questions, please use the question box. And I will start reading out the first one. So one question here is, I love the idea, but wouldn't this be an issue with ongoing deoxygenation, ongoing warming, that all the oxygen you put in will be lost very quickly again?
This is really an excellent question. Thank you. So this is really always dependent on the ecosystem where you want to reoxygenate. So there is not one way to reoxygenate. I just have an additional slide here. So these are possible techniques that are used in different environments. So reoxygenation is already used in, for example, lake environments or how do you say, reservoirs, sweetwater reservoirs. So this would be the case for the right-hand side, reoxygenation, where bubble plumes are used. And they really reoxygenate only the bottom part of the lake. They don't alter the stratification of the lake, only really small in the bottom part, of course, because we are putting oxygen in and then changing the dynamics a little bit. But the bubble sizes are really adapted to the ecosystem. On the left-hand side, we see something that is an installation in a harbor, for example, where the stratification is really not so important, because here always, if there's wind blowing over the water, the water is always mixed until the bottom. So if you think about the ecosystem that could actually profit from reoxygenation, you always have to think about how the physics of the ecosystem are made up. What's the stratification? How are the organisms adapted to the ecosystems, and what could be the future change with global warming? So with increase of stratification. For the case of the Baltic Sea, for example, this is a sea which is really strongly stratified due to the freshwater input of the catchment area and also the supply from salt water from the Nordic Sea. So we already have a really strongly stratified basin. And there, of course, the stratification due to thermal effects under global warming would get even worse. But this would also mean that the eutrophication of the ecosystem would get worse, because there's less mixing even between the surface and the bottom waters. So here, reoxygenation could actually really be something where the ecosystem could profit from. I hope I answered the question.
Yeah, thank you. Then there's a question about desalination plants. Could these be used? They are also on many onshore sites, maybe not in the wind parks, but along coasts as well.
So desalination is actually this is a really good question, because also if we produce hydrogen offshore, we have to desalinate the water. So in that way, you increase the salt content of the water that you reject into the water column. So the strategy how you put this highly saline water into the water column is really playing a role, first of all. And if you think about desalination plants that already exist, they actually have the problem that when they put in this brine, so this high saline water, which is called brine, that can actually lead to a change in stratification of the ecosystem and can even worsen the deoxygenation near the bottom. So the strategy for desalination plants that are really land-based is to distribute the water in very fine injection points, not as a one spot source, but a lot of sources, in order to keep the impact as low as possible. So it's rather a problem for the environment to put this highly saline water into the water column than that the ecosystem could profit from. Yeah.
And could you add oxygen to those streams? Would it be beneficial?
One could add oxygen to those streams, but I would really say this is again very dependent on the physics of the system next to the input points and the mixing, of course. So of course the oxygen could be added to this water, but the problem here is more the stratification than the oxygen in this water.
Yeah. Thank you. So one question, final question about the global impact. Can 0.07% of increase in oxygen really make a change?
This is a great question again, because of course 0.07% is nothing compared to what we will lose in the future. This was really a study in order to find out whether we could actually see an impact. And the fact that there could be a global impact is really supporting us in the will to do more refined local and regional studies. Because if we can already see it, I mean, this is really a scenario which is industrial and a little utopic dream, we can say. But on a local scale, this could be really a short to moderate term strategy in order to help abate eutrophication. Yeah.
Okay, great. Thank you. We have many, many more questions here, and we will send all of them to Patricia, and we will also try to help to answer. Thank you for everybody asking questions here, and thanks to Patricia for this excellent talk and very stimulating. We now move on to the second presentation by Bo Gustafsson. Bo is a senior scientist at Stockholm University at the Baltic Sea Center. And he is really the expert for Baltic Sea research, where everything comes together, heavily hit by deoxygenation because of eutrophication, river runoff, atmospheric pollution, and also by warming, which is much faster than the global mean world ocean. And so Bo will now present give another special focus on the Baltic Sea. Bo, the floor is yours.
Thank you very much. So let's see. So yes, I will talk about the Baltic Sea today. So that's what as Andreas said, that's what I know, the Baltic Sea. And most of you are maybe familiar with the Baltic Sea, but it's a rather special region. It's a large fjord basin with very narrow and shallow sills in the south and a rather large freshwater supply. It's also a rather large basin. The distance from the southern to the northern part as the crow flies is about the same as from Miami to Washington, D.C. So it's fairly long, and it also then covers somewhat different climate. Also, the catchment area is is quite diverse. So most people and agriculture occurs in the southern part, and in the north there are less people and more of boreal forests. There is 9 countries in the catchment, or actually there's 9 coastal countries, and then there are additional countries in the catchment also influencing the Baltic Sea, which also makes management a little bit difficult compared to many other areas. So first I will go through a little bit about the history of the Baltic Sea and the Baltic Sea catchment. And I would show some time slices here with phosphorus loads in the yellow graph, and then winter phosphate concentrations in the main Baltic proper basin in this other graph. And we start in 1950s. After the World War, we had a big increase in population, but also a huge urbanization. In some countries, the urbanization started already earlier, but in large parts of the catchment, it really kicked off. We had also, as the same as in other Western countries, we had the mechanization of the agriculture and also the industrialization of fertilizer, primarily nitrogen fertilizer, but also phosphorus fertilizer increased the consumption and production after the war. And we see how the loads, this is a load reconstruction, most of it, but still we see the phosphorus load increased by more than doubling in this period. And actually, already in the late 60s, it was recognized, as you can see in this graph below, that the oxygen depletion increased in the Baltic Sea. The Baltic Sea is naturally prone to hypoxia, but there was a clear trend already after World War II. However, nobody in the 70s, at least, there wasn't many people aware that eutrophication caused these changes. So it was talk about other reasons for change. However, in lakes and coastal areas, eutrophication was really mentioned. In the 80s, the society, so to say, stabilized, fertilizer consumption stabilized, and wastewater treatment plant construction intensified in the Western countries. And also eutrophication was really identified as the major driver of change in the Baltic Sea. There was also an exceptionally long stagnation period in the Baltic that caused some drastic changes in the stratification and also oxygen depletion. Then the big change, political change in the 1990s, following the collapse of the Soviet Union and Eastern Bloc, made a huge change to the Baltic Sea catchment. And it was also a period with strong economical development and political stability. And nowadays, since 2004, I think all countries except Russia are now members of the EU. However, although nutrient load started to decrease significantly in this period, the hypoxia continued to increase. And there was a massive bloom in 2005 that caused a lot of political stir. And given that also we had these new countries in EU, the optimism was such that the political society said that, yeah, well, just let us just solve the problem. And that was formulated by the Helmholtz Commission, that is the regional convention for the environment of the Baltic Sea, in what's called a Baltic Sea Action Plan. And they have the objective there is a Baltic Sea unaffected by eutrophication, qualified by some ecological objectives. And what was done was to calculate then the maximal, what's called in Helcom, the maximum allowable input, or what you could call sustainable load, to the Baltic Sea in different basins that we need to reach in order to reach this goal of unaffected by eutrophication. So after that, after 2007, actually the loads have continued to decrease for these now, and this figure is until 2020, but it's now a decade ago, or it's 15 years ago, this action plan, and the loads are still, phosphorus loads are still decreasing even today. But as you see from the phosphate concentration in the water column, not much have changed actually in the past 2 decades. And it's even so that the situation in some respects are probably worse than ever in terms of hypoxic area, and also in cyanobacteria. So there are some frustration in society when we spend so much effort. The loads have really decreased a lot. And why is this then happening, that it's so bad? I should say that there are coastal areas where the conditions have improved. Luckily, we have models. This is our model called Baltzem. There are other models that are quite similar in various with a similar concept of nutrient cycling and general biochemical cycles. So these tools can help us to understand. And one scenario we have done to communicate with society and stakeholders is to really show why it's so bad now, and that our measures have had some effect. We did a simple scenario where we kept the loads in nitrogen loads and phosphorus loads as they were in the mid-80s when they were highest. And what we can see from these scenarios, so here you have the kind of standard run, which I call reload. In the white curve, the circles are observations, and then the scenario without the reductions in red. And we see that for the nutrients on the top, inorganic nitrogen would have been more than double. In winter phosphate would have been about 60% higher. We would have had 65% more phytoplankton during summer, and 44% larger anoxic area. It is in this figure. So even though it's bad, it should have been much worse if we didn't do the effort that we have done. So, but still, what about the future? So we did some scenarios with using the most recent estimate of nutrient inputs, which is 2020 so far. And then we did not do climate scenarios here, but we did some randomized meteorological forcing to get some variability, capture some variability. And what we see, this is plots then up to 2050, and the first part of the graph is this standard simulation with the real weather and real loads, and then it's this range of variability in these runs, together with the average of the runs. And we see that winter inorganic nitrogen is actually increasing a bit. That has to do with the internal biochemical cycles in the Baltic Sea, which is where nitrate is highly controlled by denitrification and nitrogen fixation rather than nutrient inputs. Phosphate is gradually going down, but it takes a long time. And chlorophyll A is also following basically the phosphate when it goes down. And hypoxic area will also gradually go down. But there is still a huge variability so even at present day loads, we can still have bad years with as much hypoxia as we have today. And looking at these scenarios, we can also see how far do we reach according to the thresholds set up in this Baltic Sea action plan, where we should reach in different indicators. We see that in about 27 years we would only fulfill some chlorophyll with current loads, although the others are decreasing. And in 2100, we would have fulfilled 4 out of 6 of these indicators. However, it's not so surprising, since we still are not at this maximum allowable inputs. We're still exceeding it quite a lot. So this is from the latest indicator report from Helmholtz, where you can see for different basins the inputs, and this small bar, horizontal bar, is the maximum allowable input to each of the basins. And it's not too bad for nitrogen, which is on the left-hand side, but for phosphorus, we lack still a lot of reductions, especially to the Baltic proper down here on the right bottom. It's still some probably like 40% reduction needed, and that can be discussed whether that will be possible even to reach. So in summary, there are very long time scales and long-term variability in the Baltic Sea that really makes these modeling tools necessary for management of eutrophication. We saw that already in the 60s. We saw the first signs of eutrophication, and actually I didn't show that, but one test was to do a steady state simulation. You end up with the loads at about 1970 would give the same result we have today as the reload. So in already in 1970, it was basically too late. We should have started to reduce already back then to get better than we have today. The load reductions have had a significant effect, and it would have been much worse without it. And I think that is also a lesson that needs to be learned for other regions, that measures should be implemented as soon as possible, even though symptoms are not so large yet. And most likely present day nutrient inputs will give some improvements with time. The time in itself is a difficult modeling problem that we are working with. So one should take these time projections with a grain of salt, because there are some of the biochemical processes we do not exactly know. We do not exactly know how the legacy of carbon in the sediments, how that will decompose or when there will be oxygen again, how the sediments will react and how long time it will take until this excess phosphorus can be taken up, etc., etc. So it's still difficult to say, and also with that we also have the natural variability of the Baltic Sea, which is on the order of decades as well in circulation and the physics. But we still need to do more, at least if we want to reach these targets, management targets. But there is a challenge now that we just made an inventory recently that actually most of the large cities or large or medium-sized cities all around the Baltic have fairly decent sewage treatment. So for instance, sewage treatment, maybe one can do 5–10% more load reduction on sewage treatment to the total phosphorus load, but not much more. And agricultural inputs have also decreased, and it will be difficult to take very much more measures. And as the measures, we run out of cheap measures, we need also from the scientific perspective, we need to get better tools and improve our scientific basis for decision making, and also allow for good measures of a desirable state of the sea, and what kind of ecosystem services, if we say so, we want to reach, and how we can model how that can be reached and with what measures. So with that, I will thank you.
Thank you very much, Bo. Excellent presentation. This well, fascinating system, Baltic Sea, also politically, where I think some success has been achieved, some things have worked, and it's a pretty good test basin, maybe a role model for what to do with other marine systems as well. A few questions here. First question, what sets the time, the delay time between reducing input loads, nutrient loads, and recovery or stabilization of the system?
It's primarily the phosphorus cycle, which is then a combination of the long residence time of water and the fact that phosphorus basically only can end up as buried in the sediments or exported to the North Sea. It's not really so that there is a lot of, sometimes you get the notion that there is a lot of phosphorus in the sediments, which it of course is, but the turnover between sediment and water column is actually fairly fast, I think. From what we get from the models, it goes up and down with a time scale of maybe 5 years or so, but the combined system then have a time scale, at least in our model, of something like 50 years for phosphorus.
And
nitrogen turnover is much faster because there is a massive denitrification nitrification cycle, so that is just of the order of a couple of years, nitrogen. Yes. In present day, when it's so hypoxic and anoxic.
Right, thanks. And a question by Wolfgang Köwe here. What is the assumption concerning the warming trend in your projections, and how could it change the picture?
These projections are without climate change, so it assumes no warming. However, there's been done a lot of climate change projections throughout the years. But I think the overarching picture, it's changing quantitatively when you have climate change scenarios, but I think it's shown that the nutrient inputs, the anthropogenic nutrient inputs, are a larger perturbation than climate change for these overall biochemical cycles. If you look closer at eutrophication or at the ecosystem state and especially higher trophic levels and so on, you might have a massive impact, of course, on climate change. So,
yeah, thank you. Then a question about this vicious cycle that Patricia mentioned already. So if there's more phosphorus input, there could be more nitrogen fixation and even more deoxygenation, leading to more phosphate release from sediments. Do you think that could happen, is happening, might happen in the future?
I think it have happened. I think it have happened. But I mean, the big change when it came to Baltic Sea hypoxia was in the 50s and to some extent in the 60s. That was when the sediments became more or less anoxic. And there is actually a described event in 1962. There was an event where phosphate concentrations increased by a factor of 3 over 1 year, and that was actually attributed to an anoxic event that a lot of iron-bound phosphate was released. But I think at present there is so little oxygen that the amount of iron-bound phosphorus is quite small, I would say. I think most of it is gone already. So now the question is how much iron is available in the system when if it becomes more oxic. How can we get back this the iron-bound phosphorus into the sediments? And that is one of the questions I said is kind of a joker in our projections of the future.
Okay, yeah, that's interesting. Yes, thanks a lot. And then the last question is here on the comparison or comparability to issues in the Black Sea, which also is hit by deoxygenation. Do you think that some of the mechanisms are similar, that what has been learned from the Baltic Sea could be translated to the Black Sea?
In parts, yes, but I mean the Black Sea depends on what you mean with the Black Sea. I mean the Black Sea itself is of course the large area that has been influenced by or are still probably influenced by eutrophication, but we also seen that the state have improved somewhat. I'm not an expert in Black Sea, but I think that would be fairly similar responses. It's of course different timescales, I would guess. It's more open with these shelf areas, so there might be different timescales, but yes.
Okay, thank you very much. Well, one very final question about the organic carbon content in the sediments. Could that play a role? Is that some historical debt that might come up and oxidize, or take up oxygen?
Yes, I think so. I think it's documented that there is a lot more organic carbon in deep sediments today than it was previously, and some of that will break down in the future or are breaking down currently at some rate. Of course, as we see in historical sediments elsewhere where it has been hypoxic or anoxic, you get some of these sapropels, so to say, remaining. So it's difficult to say exactly how much will be remaining.
Yes.
And how much will be broken up.
Yeah. Thank you, Bo. Thank you very much for your very stimulating presentation and a very concise overview, and also with an optimistic or semi-optimistic note, I think, but there is some hope, but we have to still need management. And as you also said, won't be cheap and easy. And one has to do this very, very carefully. And possibly there's some way for industry, economy, and academia to really collaborate to help to find solutions that really work.
Yeah.
Try to share screen here. Yes. Thank you. So that brings us to the end of our 20th webinar. And please, remember, we will continue. We have next webinar very soon. Good newsletter. You can find that here. All right. Via this icon. And stay tuned for more webinars, more interesting insights, possible solutions on ocean deoxygenation, improving our understanding, but also co-developing solutions with stakeholders, with industry, informed by the best science that scientists can deliver. Thanks to our two excellent speakers today, Patricia and Bo, very much appreciate, and thanks for all your excellent questions. And we make sure that those that couldn't be answered in the short time we have here will be answered by our speakers and by us, by the GO2NE team, very, very soon. If not, send us an email, let us know, and please register for the next webinars. Have a good rest of the day. Goodbye, and see you soon. Thanks to all of you.